So today we are going to discuss about the different routing protocols. So this is a general representation of a graph, which basically consists of n routers and a set of links. So these routers are represented in this graph as U, V, W, X, Y, Z. And your links are basically U, V, V, W, U, X, and likewise. Now, what we are going to do is we want to compute the link cost. The particular link cost between U and V is basically 2. And in a generalized form, it is basically cost of sending your data from X to X dash. So basically in this example, you say that cost of sending your data from W to Z. So basically think about what is this particular cost, and that you see is as 5. And now we are going to see what is the link cost of sending a data from a particular source to a destination. So basically the sum of all the costs. So cost of sending your data from U to X, X to Y, and Y to Z. So the sum of that would be the total sum. So that will be 1 plus 1 plus 2. That is basically 4 if it is this particular route. If it is any other route, it will be a different value to it. So this is how we can write it in that particular form. In terms of algorithms, it can be classified into two different forms. One is global, and the second one can be decentralized. Global, an example to that is link state, and for decentralized, an example to that is distance vector. Another form of classification would be static and dynamic. From the name itself, static means it doesn't change. The routing algorithm doesn't change too often. And dynamic means the routing information changes in a periodic manner, depending upon the configurations or settings. So first we need to talk about the link state routing algorithm, and one of the algorithms that we need to study would be the Dijkstra's algorithm. And some of the main things that you should be noting is what are the notations. One notation is cost of sending your data from X to Y. That is, if it is connected one, it will be some value like what we have seen before. And if it is not connected, we'll be writing it as infinity. Now, dV is the current cost of that path from the source to the destination. And PV is a predecessor node, so which is a previous node to which the connection has come. N dash is something that you need to compute. So you're saying that you have to start from a particular source. So N dash will be basically a set, and the first entity would be the place from which you need to start. This is the algorithm. We have already discussed that in the earlier class, but still as a recap, you will be having an initialization. So initialization is basically you have to introduce this particular set N dash, and you're assuming a value to it because that will be a starting node. So from that place, you need to start. So N dash, the first value will be the starting node. And then what you're going to do is whichever nodes are connected to it, or else whatever relative nodes are there, what is the distance to that? So if a node that you're going to consider is V, if it is adjacent or connected, so their cost to that particular node will be what is the cost of sending your data from U to that particular node. Else, if it is not connected, you're going to put it as infinity. So this would be the starting place. Now, what happens in the remaining iterations is that after your first step, which is the most minimum of it, and the minimum node will be added to that particular list, that is N mesh. So the minimum value initially was U. Now, after your initialization phase, you will be adding your new value to it. That is, if this case, it is W or whatever it is. Now, what you're going to do is that if for this particular new node that you have added to this list, you want to compute the new minimum. So this is your Dijkstra's equation that you say. Now your the cost, the new cost would be the minimum of the two items. Which are the two items? The actual, the current minimum, or else from the new node you're going to transmit your data. If that cost is minimum, you can go to take that. So if this is minimum, you'll be retaining your values. If this is minimum, you will be updating your vector with the new value. And this goes on till your stopping criteria would be that if there are 5 nodes, you should ensure that your N dash, that means your node set should have all the 5 nodes inside that particular set. So that would be your stopping criteria. This is how your algorithm would be looking like. So just to note what are the different points in this. So this is your iteration step. This is your n dash. And what you have is you have different columns corresponding to the number of nodes in that particular network. Now this is your initialization step that you have said. That would be you have to consider which is your starting node. And once you have that, from that particular node, so from this particular node, what is the cost to the all the other nodes? So if we are taking V, it is basically 2. So that is what you're writing 2. And its predecessor node from where the connection is coming is U. So you have 2U. Now if you're taking X, it would be your cost would be 1 and the predecessor is U. So you have for X, it is 1 and U. If it is W, what you see is that the cost is 5 and the predecessor is U. So you're writing 5U. And since for Y and Z, there is no direct connections from U. So you're going to write as infinity and infinity. This step says that you have to check what is the minimum of 2, 5 and 1. So 1 is the minimum. So what you're going to do is that into n dash you add X. Now what you're going to do is that you're going to apply your Dijistra's algorithm to find if there is a least cost path to V. So your for V, what is the least cost? If it based on your Dijistra's algorithm, it is min across what with what is your existing min or what is your existing cost, or else now you have added your new node X, right? So what you're going to do is that you're going to send your data to X and then forward that to V. So this would be dx, which you already added, plus cost of sending your data from X to V. This would be nothing but minimum of your actual value, present value is 2, and this would be from 1 plus 2, that would be 1 plus 2, that would be 3. So this is your minimum. So what you're going to do is that you're going to retain 2, and the predecessor node is via U itself. So this is retained. Now you're going to take the case of W. Now you want to compute based on Dijistra's algorithm, what is your new W? This would be the minimum of your existing W, that is this, or else what you can do is that you can send your data to X and then forward it to W. So this would be cost of sending your data to, or else the minimum cost of sending your data to W plus what is the cost of sending your data from X to W. And this would be minimum of your actual cost or your present cost is 5. And this would be dx is 1. This is 1 and this is 3. So this would be 4. So 4 is minimum. So what you're going to do is you're going to update the least cost, that is basically 4. And it is not via U going to go, it is via X. So you're going to update this as X. So this is X. Now what happens is that the next, since this is added, so this is going to be kept blank. Since this is added, you're going to keep it as blank. And now for Y, again, the same Dijistra's algorithm. Your same Dijistra's algorithm. You want to compute what is your new cost of sending a data to Y. So minimum of your present cost, or you're going to send it to X and then forward that to Y. So this is it. So this would be, so this is the path we're going to take. You're going to send it to X and then you're going to forward it to Y. So this would be minimum of your original cost was infinity, or else this is X is 1 plus 1 from X to Y is 1. So that is basically 2. So this is what you're going to write. You're going to write as 2, and then your predecessor node is X, and to Z there is no path yet. So you're going to put it as infinity. Now this algorithm goes on. From this row, you're going to find out which is a minimum. So you can either use this particular 2 or this particular 2. Since this algorithm takes this 2, this continues like that. So you're going to add Y to this, and with this particular Y, is there any alternate route to reach V? So your current cost for sending your data to V is 2 via U itself. Now you're sending your data to Y, and there is no actual path to sending it to V, so that would be infinite. So this would be minimum still. So you have 2U. Now for W, if you want to rewrite for W, what happens is that we'll just write it for W since there's a change. So your new W is dW would be minimum of your existing W which is basically T, or else now you have your data till X, Y, right? So that is basically cost of sending a data to Y plus what is the cost of sending a data to Y to W. So this would be minimum of, now your current cost of that is basically at this step, your previous cost is 4, right? So this is 4, or else now you can send it to Y, that is your cost is 2 plus Y to W is 1. So 2 plus 1 basically is 3. So your new updated value would be 3, and your predecessor node to W is Y. So you have 3 there. And for Z, now you have Y, right? So for just for your understanding, now for Z, what you have is minimum of your current D is it, or you can send your data to Y and then from Y to Z. So this would be basically minimum of infinity, or till Y it is 2, and from 2 to Z is basically, sorry, Y to Z is basically 2. So you have 4. So that is there 4. So what you can write is, you can write it as 4, and your predecessor node is Y. Now from this again, you're going to see which is your minimum. So you have taken 2, 3 or 4, 2 is minimum. So you add that to this. And then you're going to see if with this particular U, is there any shorter path to go to Y? No, this is the shortest. So 3 is retained. And for Z, you're going to see if this particular V, is there any other alternate path? No, nothing more. This is the shortest. So 4Y. And finally, you complete that whole thing. So this is your stopping criteria. What you see as your stopping criteria would be that you have all your nodes in N dash, U, X, Y, V, W, Z. So how many count are there? That much count of nodes should be there in N dash. That would be a stopping criteria. So once this is done, you have all the routes that you know from your source to the destination. So this is the tree that you want to draw. So from, if you want to go from U to V, this is the path. If you want to go from X to X, U to X. If you're going to go to Y, you have to go from U, X, and Y. If you want to go to W, it is U, X, Y is W. And if you want to go to Z, it is U, X, Y is Z. How do you get this? It is based on this particular thing. So based on your final representation, if you want to go to W, it should be via Y. So it will be reaching not by any other parameters, its predecessor node is Y. Now, in the case of Y, you say that its predecessor is X. So from if you want to reach Y, it should be via X. If you want to reach Z, it is via Y. Now, if you want to see W, so your W is again Y. So what happens is that you have to W, the predecessor node is Y. So you're going to draw it like this. And how do you reach Y? Via X. And how do you reach X is via U. So this is how you draw that particular tree. And this is the forwarding link. If you want to go to X, it has to go through this particular adjacent link. If you want to go to Y, you have to forward it to X. If you want to go to W, again, you have to forward it to X. If you want to go to Z, you have to forward it to X. So this is your forwarding table that you come across. Okay. So these